So, all right. Well, yeah, since the start of the new calendar year, my name is Steve Martinez. I am your chapter president. I work for the University of Oklahoma and the National Severe Storms Laboratory. Um, I don't think Greg made it online. He is our vice president. Dave is on if Dave wants to say a quick hi. He's our secretary.
Hello, everyone.
And here's our man Stanley. He is our treasurer. So I'm glad you all could be here for this month's meeting. So first up, I know this is a week later than what we usually hold it, just because of the AMS annual meeting that was this past week in Denver. Amazing attendance. They set a registration record for 6,700 people attending the AMS meeting, and 5,300 were in person. So there was a lot of faces and a lot of discussions to be had there in Denver, and it was great for the community. And one of the faces that I got to see and got to talk with real quick is our speaker for today, and I'd like to introduce Dr. Chris Weiss. He is a professor at Texas Tech University. He's been there for 18 years. He has gotten his degrees at the University of Michigan and the University of Oklahoma. A lot of his research involves convective meteorology, everything from dry line processes to deep convection, especially how to deal with tornado genesis. Probably one of the biggest things he's known for is working with a lot of the field campaigns that's helping over the last 10 or 15 years. That included Vortex 2, Vortex Southeast, which is now Vortex USA, Perils, and Taurus. And he has a lot of great hobbies, and probably one that we're all accustomed to, which is watching our favorite college football team struggle in vertical games. So without further ado, the floor is now yours, Dr. Weiss.
Thank you. Yes, it has been a rough year for football. I still recovering from that Michigan game, although you folks are probably pretty happy out there in North Texas with the outcome, but I'm still reeling from that one. Can you guys hear me okay?
Yes, sir.
All right. Let's see if you can see me okay. All right. You can still see that slide okay?
Yes, sir.
Yes.
All right. Great. Excellent. All right. Well, thanks a lot, Stephen, for the introduction. And similarly, it was nice to meet you at AMS. And thanks for the invitation to speak with you all here today. The title of the talk here is kind of purposely rather flippant. Cold pools. We understand that cold pools, of course, are very important for our severe storms, for maintaining their intensity, for their propagation and whatnot. We're going to take a dive into these processes here tonight. And I'm going to kind of look at it kind of a two-pronged approach. We're going to look at it for upscale modes, specifically QLCSs. And we're also going to look at it for the three-dimensional modes, for our supercell modes. And we'll take some time, review some background. I realize most folks on here aren't reading Holton every day, so we'll throw a couple equations in there, but we won't get too deep into that. Establish some of the theoretical framework and talk about some of the numerical simulations that help support our understanding of cold pool processes as related to, say, vorticity. And then we'll also talk about observations, and that directly hooks in the last two field campaigns that Stephen mentioned in the intro there. The Perils project, part of Vortex, USA now, and the Taurus project, which is an NSF project that we have been involved in for the last few years. So I'll talk about both of those in time. Before I go any further, I want to acknowledge the three names listed here. These are students in my group at Texas Tech that have contributed some of the material that we'll be discussing here today. Let's see. There we go. All right, so very simply with cold pools, I go back to my title slide here. I could overlay a guess as to where the depth of the cold pool that might accompany a storm such as the one we see here. This is actually from 2019 up in Imperial, Nebraska. Nice mothership supercell that we had for Taurus. And I feel fairly confident putting it at the level I did, based on the location of the tail cloud we see off here to the down shear side. something like that, something we typically see in the lowest couple kilometers. The processes that drive our cold pool, of course, I think we know the usual suspects. We all know about evaporation, of course, but really any phase promotion. So melting, of course, is also it also contributes as well. We often forget that. So that the types of things we look at, of course, when we're forecasting cold pools, LCL height. We know the greater the depth of our subsaturated layer, typically the stronger our cold pools are. The specific and relative humidity in that layer, of course, the melting level, dynamic perturbations, anything that's driving vertical motion that can affect the residence time of hydrometeors in our, say, in our subsaturated layer. Vertical wind shear, that drives things like size sorting, and that can affect the distribution and the magnitude of cold pools as well. So it's rather complicated. That's why there's a lot of folks that are studying it, like I am, and my group is. If we look at our vertical equation of motion, we understand, I think even an intro Met student can quickly grasp the last term on the right-hand side here. We're looking at vertical accelerations, and we know buoyancy obviously has impact on that. We basically, the ability of our parcels to achieve level free convection, that's one example. We know that that's a failure mechanism often for the sustenance of convective systems, tornadogenesis. Think of the Goshen County storm, and from Vortex 2, the inability to achieve LFC was identified as a mechanism that was driving the dissipation of that tornado. And then we get back into this first term on the right hand side. There's these dynamic pressure gradient forces, and this is a little bit more difficult to understand, and you have to go into the original equations of motion, the Boussinesq equations, and you discover that there are other things that can contribute to pressure perturbations, like vorticity itself. Anytime we have vorticity about any axis, horizontal or vertical, that's associated with low pressure, and as a result, we can drive dynamically. We can drive pressure gradient forces and accelerations that are important for our storms. And that first term on the right-hand side is also partially affected by, well, I mentioned it's partly tied to vorticity. So it's important to take a look at vorticity equations to understand not just vorticity, but also, of course, vertical accelerations. So when we look at and I promise this will be the last equation here. We look at the vorticity equation, time rate of change, the usual suspects here: tilting, stretching, the viscous term, something we're really starting to appreciate here in the last decade or so as we are able to resolve these boundary layer processes better, and we have observations that are closer to the surface. We appreciate that friction is an important contributor to vorticity. But I really want to zone in on this third term here. This is the baroclinic term. And for the life of me, I've been in this a number of years, and I still don't know why we write it in terms of this alpha term, the specific volume term, but that is a gradient in air density cross product with the gradient in pressure. So basically, simply put, anytime we have gradients, for example, horizontal gradients in air density, that gives us an idea that there could be vorticity generation afoot. And that's of course, via what we just discussed in the last slide. The generation of vorticity feeds into this pressure perturbation term and affects vertical accelerations. So that's why we care so much about processes like baroclinic processes. So if we're going to understand vorticity, we need to understand baroclinity. And to understand baroclinity, of course, we need to understand our cold pools. And that gets us into the subject matter here. I think it's useful to, before we start spinning solenoids here for the next half hour, just to understand the process of baroclinity. It's I think it's something that can be grasped fairly easily with a good conceptual model, hopefully like this one. But if we look at just kind of a height cross section here, and we have this material circuit, and I guess let's just say it's a beach ball. Okay, we have a beach ball circuit here, and when we look at the two terms of that cross product, again, grad rho cross grad p, if we're dealing with a homogeneous atmosphere, those vectors both point the same direction. They point downwards in the direction of quickest increase. And so there's no cross product, of course, if the vectors are parallel. So we don't have any spin that comes about. And certainly if we place the center of mass in here, it'll be just slightly below the geometric center of the beach ball, if you will, because of the density increase as we head downwards. But if we present a situation where we have this horizontal gradient in density, for example, if we have an inflow state here on the left-hand side and a colder, more dense outflow state on the right-hand side, well, then that center of mass, the weight in the beach ball, if you will, travels, and it travels to the right side of my circuit. And I'm sure a lot of folks here probably have played with weighted beach balls. I have 2 kids, so I have done this often. If I move that beach ball, if I hold on to that beach ball with that weight on the side and I let it go, we know what's going to happen, right? It's going to rotate and such that that center of mass comes back towards the center, right? So when we connect the dots from the beginning to the end, we can say that horizontal gradients of air density in this case beget horizontal vorticity, or this spin about this horizontal axis. And that's a big deal. When we're trying to understand, what's sourcing tornadoes, for example, anything that's generating spin is of interest to us, especially things that are generating spin close to the ground. And since our density currents in our cold air, they like to reside close to the surface, that's something we need to pay very close attention to. And if you just want to check out the cross product there, get your right hands ready, and you can carry that out, and you can find that your thumb is indeed pointing into the screen. That's the direction of the vorticity. Your fingers are pointing in the sense of the spin itself. And let's see, since we're going to be dealing with a few vortex lines in here, just a reminder how that works. The vortex line is always parallel to the vorticity at every point. So in this case, in your screen, your thumb's pointing straight into the screen, and so does the vortex line, okay? So imagine a line going infinitely in and out of your screen, or from out of your screen into your screen, and that's the vortex line in this case. One other thing I have to get out of the way here at the beginning here, this matter of flavors of vorticity, since we're going to be talking about streamwise and crosswise vorticity today, just a reminder how that works. It's again, it's our beach ball, our vorticity vector in this case, which points into the screen. If that is parallel to the storm relative flow, then we say that is streamwise vorticity. And that vorticity is very important for us because that is stretchable vorticity. Our vertical accelerations are co-located with where the vorticity is at, and therefore that's stretchable. That's opposed to crosswise vorticity, where we have orthogonality between the vortex vector and the storm relative flow. You still generate vorticity that way, but it is largely not stretchable, not like streamwise vorticity at least, okay? So just to keep that in mind, streamwise vorticity is good for our vorticity intensification, for tornadoes. Okay, all right. Let's chat about our 2 modes now. So I'm going to start out here with these quasi-linear convective systems. And I think we've all had some experience with these. We see here an example from one of our early cases in vortex, when it was called Vortex Southeast over northern Alabama, a QLCS case that raced through the Tennessee-Alabama line there. Each of these locations here, these are sticknet stations that you see reporting. We'll talk about sticknet here in a little bit. But this particular case was interesting for a couple of reasons, but probably in addition to just having a QLCS, we did actually have 2 mesovortices, 2 principal mesovortices that formed on the kinks here in the line, and both of those were tornado warned, as they typically are. Turns out the northern mesovortex was non-tornadic, and the southern mesovortex ended up being tornadic, albeit weakly. It was tornadic, so it allows us to make some comparisons here of the environment and the cold pull properties say we're comparing the tornadic and non-tornadic mesovortex, and we can also compare the mesovortices to the rest of the line that's largely not rotating. You can actually see a photograph from our position. We're between the mesovortices, looking towards the north. And you look at that and you kind of squint your eyes, and it looks an awful lot like an RFD cut on a supercell, and there's a lot of processes that are probably quite similar there. So before I show some results from that, just to review, since our subject is cold pools here, what we understand about cold pools and vorticity generation in these quasi-linear convective systems. And some of our early papers, our seminal papers, I make it sound like it was decades ago, but it was 2003, invoked baroclinity very directly. Just very simply, we generate vorticity along this cold pool edge, just like the beach balls that I showed a few slides ago. And we can tilt those vortex lines with a downdraft within the convective line. And by golly, we generate, these vertically tilted vortex lines, which means we have some, vertical vorticity. In this case, we end up with, an anticyclonic member on the north side and cyclonic on the south. And I think, some of the scrutiny in the literature with regards to these processes, this process in particular is, often we don't see that exact directionality in the couplets with regards to the surge of the cold pool. So there's certainly other theories out there. Nolan Atkins and St. Laurent in 2009 also invoke baroclinity on that leading edge of that cold pool. So we've got beach balls in play again. And but this time we're tilting via the updraft that's forced on the leading edge of the cold pool. And that gives us, I guess the sign of the vortices that we more often see. Although a lot of times it seems like we do favor the cyclonic member, and Coriolis accelerations, of course, help us out with that. More recently, Matt Flournoy and Mike Caniglio had a great paper looking at sources for a mesovortex. And they found actually 3 separate mechanisms in play. One being environmental, this crosswise vorticity that rises from parcels coming in from the environment. Streamwise vorticity that comes in from the rain-cooled air from the northern side here. Processes that will be similar to maybe to things like the streamwise vorticity current that we've been, that we'll be talking about later here in a few slides. And then this generation of vorticity and this descending current in this rear inflow jet, which is what we call vortex line slippage. And that's a process that's gained a lot of attention in the literature, and something we're very alert to. Basically, it'll take me a half hour to explain the whole process here, but just understand that if we generate horizontal vorticity for a descending parcel, that when that parcel hits the surface, that vorticity tilts upwards. So what's horizontal vorticity during the descent very much becomes vertical vorticity when we actually get close to the ground. And that's a big deal, of course, when we're trying to generate strong vertical vorticity near the surface. So that process is certainly in play in this, at least in this study right here. All right, so all these processes we talk about here, almost all of them, invoke baroclinity in some way. First of all, we really need to establish, I think, observationally whether the vorticity that we see associates with baroclinity. In other words, where we see stronger cold pools, stronger gradients in air density along cold pools, is that also where we typically see the stronger vertical vorticity? Seems like a fairly simple observational goal, but it really hasn't been carried out in the QLCS realm, not in depth at least. And that was really one of our charges in perils, which I'll get to in a minute. But back on this 2017 case, which I already showed, I can see some figures over here on the right-hand side, objectively analyzed fields from this case. And Jesse McDonald and I published a paper on this a couple of years ago, looking at again, these cold pool properties in relation to the mesovortices that developed. And what we found in that case, and this is probably best illustrated in this upper right case, this is the gradient in what we call virtual potential temperature. Just think of that. Anytime you see theta V, just think of that as density, as our stand-in for air density. So we're looking at gradients in air density normal to the cold pool edge. So where we have the quicker changes in air temperature or air density, that's what's being colored in the deeper shades of blue here. So our weaker gradients are the whiter colors, and our stronger gradients are these blue colors. And sure enough, what we found in our case when we're contrasting the non-tornadic and the tornadic mesovortex, there's a pretty clear difference in the magnitude of this gradient. Much stronger gradient here for this southern member that produced the weak tornado near Cullman, Alabama. That was one of our principal findings, which seems to give some verification to the role of baroclinity perhaps in generating some of this vertical vorticity. We also found, if you compare the mesovortices to the rest of the line, this is, you look at theta E or theta V, the magnitude of our gradients, the magnitude of our deficits is much greater when we actually talk about the non-rotating parts of the line itself. So the region between the mesovortices has a lot colder air than what we see near the mesovortices themselves. Okay, so that's two of the findings we had. This is one case from 2017, and it was hard to make general conclusions based on that. So that really was a charge for us in the Perils project here. So now that I've set that up, the Perils experiment, many of you probably have heard about it. The first year was last year. We had 2 months of field work and 4 IOPs across the Southeast. It's really the first time that we've really had such a dedicated effort to observing QLCS modes. It's a lot of challenges with that. It's in the middle of the school year and you've got students out there that are taking classes, and there's all the things that make field work in May and June so attractive, being out of classes. It's the exact opposite when you try to do this in the in the middle of a semester. But we did I think a pretty good job with it. Year 2 is right on the doorstep. It's really on the doorstep, only a couple weeks off here, and I guess that's why I have bags under my eyes right now. And well, I also have kids. I guess that's partly to blame too. But we're doing a lot right now to prepare for this. But I think we're going to be ready in time. And so we're really focused in on the QLCS dynamics. What we're bringing to the project are these Texas Tech StickNet probes. You can see an example here in the lower left. Basically engineering tripods with a bunch of weather instrumentation. So we get wind, we get temperature, pressure, humidity, we get all the state variables. The box here is kind of our central nervous system that has all our software that drives the instruments, and of course the logging of the data and the telemetry as well, so we can see things in real time. We have 24 of these. We have 48 total, but half the fleet, 24, is what's dedicated to the Perils project. And in the bottom right here, you can see the logistical mess that is scouting for stick nets in the Southeast. It's there's a lot of, even in these particular areas, and these areas you see are specifically chosen because there's a good line of sight. For radar coverage, we can see a decent ways with these mobile radars. But even within those areas within the Delta and the Black Belt, we still need to find spots that the stick nets can sit, where, we're not sitting in the shadows of, gigantic tree canopies or buildings or something like that. So we need to aspirate our thermal measurements, of course. When we look at the outcome from year 1 here, it was very successful. We had 4 IOPs. I won't go through all the abbreviations here. I'll just talk about the kind of the top line here. And this is based on work that my student Josh Ostaszewski is leading right now. And we counted 98 total cold pool intercepts from StickNet in year 1. We had a 15 kilometer halo around the mesovortices that we identified. If we had StickNet measurements inside that halo, we considered that a mesovortex sample. And using those criteria, that criterion, we end up with 52 mesovortex samples, which we're really, really happy with. And 12 other samples of the linear portion that's not rotating. Lead supercells, we had quite a few of those, especially in these first two IOPs. So we had 7 supercell mesocyclone intercepts as well, and mixed and hybrid, or I won't get into in great detail here. So very much a success. Looking forward to building on to that in year 2. Now, to give you an idea of what we found so far, and this was actually was presented just recently at the Severe Storms Conference out in Santa Fe. And this is just one part of it, but we're trying to understand, or we actually have a number of hypotheses we put forward, and I'll try to outline a couple of our findings here. So there's strong evidence, statistically significant evidence, that the magnitude of our air density gradients, our theta, our virtual potential temperature gradients, is greater in the rotating portions of these lines, these QLCSs, than in the non-rotating segments. So you can see in the upper right here, again, this is the air density gradient. 0 is at the top, so we get stronger gradients as we head downwards. And we see for our non-rotating category here, we have much weaker gradients than we do for the rotating portions. So again, that lends credence to this idea that baroclinity is definitely important for the existence of rotation in these mesovortices. And that's in line with a lot of the theoretical and numerical work that's been produced up to this point. There's also statistically significant evidence that if we compare tornadic and non-tornadic samples for mesovortices, these are all mesovortices, tornadic versus non-tornadic, that we do see stronger gradients when we are talking about the tornadic mesovortices. So the same argument that we just made for the mesovortices themselves also applies to apparently the tornadic potential of these mesovortices. And also strong evidence here that when we're talking about the actual deficits themselves, theta V prime, the air density, the total air density deficit, and the equivalent potential temperature deficit, you see a large difference here in the population. So basically, the way it reads here, for the rotating mesovortices, we do see stronger deficits in play, which is a little bit contrary to what we found in the 2017 case. But this is over a much larger sample, which is interesting in its own right there, I think. So those were interesting results to see, and we certainly look to build upon that here in year 2 as we go forward. If you're wondering about directionality, this plot takes a little bit here to set up here. This is distance relative to our stick net, and so when we're looking at these orange lines here, we're looking at samples that are off to the north of our mesovortex, and blue here will be to the south. And again, 0 is on the right hand side, so the stronger gradients. And again, we're looking at those air density gradients down here. They get stronger as we head towards the left hand side here. And I think when you just kind of at first glance here, you can kind of make out a kind of a bit of a V pattern here, where we see our strongest gradients very close to where the mesovortex resides. And as we get further away, we see weaker gradients. So that'd be our first result here, that the strongest air density gradients are found near the mesovortex, and not necessarily at the time the tornado is happening. And that's the TOT is time of tornadoes. So when you see the circles here, that's near when the tornado is happening. The squares here represent samples for mesovortices that have produced a tornado or will produce a tornado, pre or post tornado mesovortices. And we actually found stronger signals with those squares. And you'll see that we mentioned that the air density gradients again are stronger, closer to the meso vortex. When we look at directionality, especially when we talk about these mesovortices that have a history or will produce a tornado, these squared boxes, we definitely see an indication that our our gradients are stronger on the north side of the mesovortex than the south. I think we can all see those red squares are further to the left up here than the blue squares down here. And that's we think that's interesting, and it may indicate the importance of the the storm relative flow. We know that in these cases that we have storm relative flow that has a northerly component, so coming from, say, the northeast. So that means that we may be talking about air parcels coming into the mesovortex that are acquiring that vorticity, moving through the beach ball, if you will, for a certain length of time or space before entering the mesovortex. And that directionality, given that the storm relative wind is from the north, implies to us that that maybe we are seeing a process by which we're accumulating that vorticity on the way into the mesovortex. Once we get outside 10 kilometers, there isn't much directionality signal there. It seems to be stuff that's within about 10 kilometers where we see that signal. All right, quick check on time here. All right, we're in good shape. So I'm going to put the upscale mode to bed here for the moment, and we're going to switch over to the supercell mode and what role cold pools play in vorticity generation here. Compared to the upscale mode, there's a lot more in the literature with regards to baroclinic processes, but we're going to review a couple things here. I think first and foremost, this diagram from Markowski and Richardson is great because I've circled two areas of vertical vorticity in here. And these two areas are most certainly not equal. They're not the same thing. Contemporary thinking in tornado genesis and supercell vorticity is that when we're talking about mid-level mesocyclones, when we're talking about that storm scale rotation, we're largely talking about the tilting of environmental vorticity. So let's focus on this for a bit here. So the mid-level mesocyclone is driven by what we think are barotropic processes. Again, vertical wind shear in the environment. This is good, right? These are things that we can observe. These are things that we can forecast well, and that's why we're pretty darn good at forecasting supercell mode compared to where we were a couple decades ago. We have a pretty good handle on the generation of mid-level storm scale vorticity, and it's tied to the typical forecast quantities that we all know and love, our bulk shear, storm relative helicity. And when we look at soundings with big looping hodographs, we know that they're capable of producing strongly rotating supercells quite well, because we know that when we have looping hodographs that are environmental vorticity, which is orthogonal to the shear vector on the hodograph, is parallel to the storm relative flow, the blue and white vectors in this case, which of course is our streamwise vorticity like we saw in the diagram a few slides ago. And why is that important? Well, we can certainly tilt and stretch that vorticity just fine. And owing to the dynamic pressure, we know that vorticity is associated with low pressure, and that can enforce what we call dynamic suction, or vertical accelerations that are dynamically induced. And that's, boy, when you're talking about these storms, we all know, right? The low levels of these storms are generally pretty cold. When outflow starts, cycling back in to the updraft, especially, we know there's a lot of negative buoyancy, a lot of inhibition down low. So we need to have dynamic processes to force that air up past the level of free convection to keep our storm thriving and allow our ability to continue to stretch vertical vorticity. This area loft, of course, is where we typically have radar coverage for typical ranges from the 88D. So we do see mid-level mesocyclones quite well, but we must keep in mind, of course, that that's not the tornado. That is the storm scale rotation, and that is probably driven by a fairly different process than the near surface vorticity that we would see in a tornado. And that bears out in a lot of different ways. Here's an example from Jeff Trapp's student from a couple of years ago, and they're just plotting EF rating against mesocyclone, delta V, and there's an association, but it's not perfect by any stretch. No pun intended there. So we understand that the storm scale processes are important. We need to have vorticity aloft to help drive vertical accelerations, but there's a lot more in play when we're talking about tornadoes. And that brings us on over to the other side here, this other area of vertical vorticity nearer the surface. This relates to the in, up, and out problem, which you may have heard before. Excuse me. Anytime a tornado happens, it seems like some variation of this diagram on the left appears in print or online, where we have a spinning vortex tube. That's a barotropic process, of course, and that's fine. We know that horizontal vorticity is generated, and even the second panel is fine. We tilt that in the vertical and we generate that vorticity. The problem comes in between panels 2 and 3, where we somehow generate that vortex near the ground, and we know that there's some issues there because the vertical vorticity isn't strong via updraft tilting until we get well up into the mid levels of the storm. So how do we get that tornado out of there? Well, we have to either build it down from the mid levels, and there are certainly processes in the literature that describe that downward building, the dynamic pipe effect from trap, for example, where we enforce cyclostrophic balance and we bring the vorticity down. It's a very slow process. It probably happens in some cases, but most cases, it seems like something else is acting much more quickly. If we look at rapid scan radar observations from, this is from Mike French's, I think, seminal paper on the topic, and these points here, we're just looking at height versus time and basically TVS detection. And you see that as you move forward in time, quite clearly the tornado vortex is building upward with time, and not in this downward manner. So if the vorticity isn't building downwards from aloft, then the only other option is that downdrafts must be important for producing that near surface vertical vorticity. And here we are, we're back to baroclinity and cold pools and beach balls. And you can look in the diagram here on the right-hand side, and you can see an example of a vortex ring that would be responsible, that would be a result of a baroclinic process. It's basically like we just grab the front of this vortex ring by the shirt collar and pull it up into the updraft. And that's what gives us this vertical vorticity that we see circled in red here. And we think almost all contemporary thinking on tornadogenesis invokes baroclinic processes in some way. So the key considerations here: where's the cold pool? How strong is it? Same kind of things we were talking about with the upscale mode, and key observations we really need to have. And I hope ultimately in an operational setting, we can make that kind of information available in a meaningful way to forecasters that are, they're in the hot seat. They have to make a decision on, say, tornado warnings. And that's certainly one way I can envision things like false alarm rate being, improved considerably. So things like drop size distribution, we know that cold or small drops evaporate more readily, which is, of course, lends itself to stronger cold pools. So that's why a lot of these projects that we see out there, we have distrometers out there measuring rain size drop distributions in addition to all the other instruments. So in parallels, we have the same kind of setup. All right, so where's the baroclinic vorticity come from? That's relevant to the tornado. Well, you get a lot of answers to that. And I'm not going to go through all the answers here today, but one area that's gained a lot of attention over the past couple decades, well, actually all the way back to Klempen or Tuno's work, is this area in the forward flank. So we're looking at a supercell thunderstorm here. And of course, this is on the right-hand side. This is the forward flank region. And we can envision on the edge of that rain-cooled air. Here we go again, beach balls, lateral gradients, and air density, which allow for the generation of horizontal vorticity, which can be relevant to some portion of that vertical vorticity for sure. As numerical simulations have grown as our computing power has grown, I should say, and our ability to resolve smaller and smaller scales of motion has improved, we've actually discovered some features that we weren't really aware of, at least not of this magnitude. And one of those is the streamwise vorticity current. And this is from Lee Orff's original paper on the topic. And in the picture, you can kind of see the presentation here is kind of, well, we're looking towards the east. So we're kind of behind the storm looking towards the east. And what they've colored here is streamwise vorticity. And you can see this ribbon of strong streamwise vorticity that sits very low, close to the ground in the lowest, 500 meters, let's say. And that gets tilted up into the main updraft here, and certainly assumes some portion of the low and probably mid-level mesocyclone. Also happens there's tornadoes in these simulations, and there's, of course, the question immediately arises, are those related, the streamwise vorticity current and the tornado itself? And that's really motivating a lot of the work that we're doing. So my student Alex Sheath in my group, we looked at some high-res simulations following on Lee Orff's work. Really trying to get at the forcing for the streamwise vorticity current, which you can see an example of the streamwise vorticity current here. This is two views of the same simulation. I tried to show the left panel is more like a chaser's view here from the southeast, and then another one looking down the axis of the forward flank convergence boundary. And the colors here represent air density, density potential temperature, and the purplish kind of silverish hue here, this is the streamwise vorticity. And you can just see this river, this current of streamwise vorticity that gets generated on the edge of this rain-cooled air and gets tilted up into the vertical. And it turns out that these other little silvery things here, these are tornado-like vortices, that that develop. And again, can we say that the SVC causes the tornado? Well, it's hard to answer that, and that's why we're trying to uncover some of this work right now. But currently, we're really focused on what's driving the streamwise vorticity. Kind of in the spirit of, can we predict it better? And we look at this numerical study, same simulation, the animation I just showed you, but we're looking at a few static panels here now. And this left one here is just a time series, and this black line represents our reflectivity contour here. So we're basically looking at the Hooke echo with time as we go forward. And you look at the green colors here, that's the air density perturbations, and we're getting colder with time. And I don't know how well this projects in your room right here, but we're looking at two things here. The vector, the red vector here is the vorticity, and the barb represents the storm relative wind. So when these are opposite one another, since we're talking about barbs and vectors, that's streamwise vorticity. And if you can't see it, just take my word for it as we go forward in time that we do have very strong streamwise vorticity that develops. You saw that in the animation with those purplish hues. We take some cross sections through the model simulation. We go across this area down shear of the mesocyclone, where we have this the streamwise vorticity current. You can see the streamwise vorticity in these panels. The stronger orange color here is the strong streamwise vorticity. Again, we're looking in the lowest 500 meters here, so pretty shallow phenomenon. You can see a strong pressure perturbation, about 3 millibars, that matches that strong streamwise vorticity. Again, dynamically induced low pressure. So yeah, that's great. We have lots of numerical simulations now. Well, a couple examples of numerical simulations that resolve this streamwise vorticity current feature. Okay, the question is, of course, are these things actually observed? Before I get to the observations, one more thing I wanted to show here, this just looking at trajectories in the streamwise vorticity current. So these are all individual trajectories that are going to ultimately end up in the updraft region. And we release these upstream here, and they flow through our analysis plane. And what we see here is that we have a contribution, from stretching, and we have a contribution from baroclinic processes. They aren't necessarily overlaid. These are different populations here in the blue and the purple. And the parcels that end up getting the maximum vorticity kind of right in the middle here between this baroclinic regime and this stretching regime. So baroclinity seems to be important for the generation of the streamwise vorticity current, but there's also just really, really strong horizontal stretching. And when you have big area of low pressure associated with that rotating supercell, you are going to get strong horizontal accelerations. So it does make sense. Horizontal stretching is going to be a big player. We found that if you actually look at the density current structure, if you've seen density currents in labs, you know that a lot of times you get what we call these Kelvin-Helmholtz waves that sit on top of the cold air interface, kind of roll up going backwards. You can see a better picture of it right here in this schematic. We find that the vorticity associated with those billows, those KH billows, is actually very important for the streamwise vorticity current. So it's really kind of neat that this kind of persistent feature in density currents is so strongly tied to the vorticity of the supercell itself. Okay, and then here's a schematic kind of outlining what I just presented here. Again, the density anomaly here in blue, the streamwise vorticity in orange. That's the streamwise vorticity current here that we see in orange. And if you take a cross section through that, again, this kind of KH billow and the separate regimes with the stippling and the dashes here, indicating the two regimes of parcels that are coming into the updraft, and the baroclinity is relevant, especially for this area out ahead of the density, just out ahead of the density current here, but again in the lowest 1,000 meters. So what do the observations tell us? That's great. We have these simulations that give us this information. What do the obs tell us? And that's where the Taurus project comes in here. This is well, yeah, it's supposed to be 2019 and 2020. You know what happened. COVID shoved us off here to 2022. But the thing we were really focused on was the streamwise vorticity current and what we can actually, observe with the, in our case, the Texas Tech KA band radars. This is our group shot from 2019 before the world fell apart. And yeah, you can see everything out here, mobile radars and mesonets and a lot of NSSL and OU vehicles out there. And here are the unmanned aircraft, which were one of the unique instruments for the project that helped us get measurements up off the ground, the in situ measurements. So I'm going to show you data from the mobile Doppler radars at Texas Tech. This is, I guess, our publicity shot here, the lightning strike. Yeah, this is also the Imperial Storm. It's a lot like the Doppler on wheels, just a higher frequency. So we can, we can't see as far into storms because we attenuate, but the trade-off is that we can see with a much finer beam, so we can see things that are closer to the ground since we have higher resolution. Here's the other instruments involved, including the P3, which that was a great addition to the project, somewhat last minute. To give us kind of a broader storm scale context for what we're seeing with the other instruments. And here's a shot of the unmanned aircraft ingress to a supercell thunderstorm. Just eye candy here, had to throw that in. Our deployments, yeah, we travel lots of places, lots of miles, thousands of miles, lots of gallons of gasoline, which got a lot more expensive in 2022. Basically double counting every mile on my budget that I wrote for this project. It was written in 2017. So yeah, that was a tough one. All right, so the observations of the SVC here, this will be my last topic here in the presentation. Again, this is the Imperial Storm. And this is imagery from my student Alex Sheath. Hopefully this animates. Yes, we're doing good here. So you can see this tail cloud, and if you look real carefully, you don't even have to look that carefully. We see really see that sense of horizontal vorticity, and we're seeing, of course, the upward branch condensing here. So all that all that streamwise vorticity current stuff that we discussed in the simulations, at least visually, seems to bear out in this particular case. If we look at the radar imagery from this case that corresponds to the video here, yeah, sure enough, we see the KH billow. We see this rotor circulation and this vorticity, this vortex that's centered about 500 meters above ground level, just like we saw in the simulations. So this is clearly a case where we have a streamwise vorticity current, and you can almost picture the vortex lines tilting upwards into the vertical and contributing to the vertical vorticity of the supercell itself. Let's see. So what my angle on this, recently I've been trying to catalog all our RHIs from Taurus 19 and 22. And so far I've gotten through all the 19 cases and one of the 2022 cases, the Morton, Texas case. And I'm taking all the RHIs that I can find that are down shear of the mesovortex in this forward flank region, left flank region. And I'm compositing them all together to see if, among other things, if we can associate the kinematic depiction of horizontal vorticity, like we see in this image right here, this radial velocity cut right here, associating that with the vertical vorticity in the in the storm, the mesocyclone itself. So to make that association, I have to measure vertical vorticity somehow. So I just used the MRMS product, and thanks to Tony Reinhardt for his help with this at NSSL. And that gave me a nice metric to associate with the horizontal vorticity that we're seeing with the Ka radars, and see a reasonably Gaussian distribution of the vertical vorticity for all our cases here. So our hypothesis stated clearly here that the low-level mesocyclone intensity associates with, again, our resolved horizontal vorticity from our RHIs with the Texas Tech Ka radars. And I won't set that up anymore because I've already done that. So what I've done here is I've taken our entire stockpile of 450 RHIs and I split them into quartiles according to the strength of the mesocyclone. So this is our lowest quartile, our weakest mesocyclones. What does the depiction of the outflow look like from the Ka bands? And so just to orient you here, since you probably haven't seen these before, our inflow here, our radar is positioned somewhere off to the left-hand side. Of course, the position varies some, but the red here represents inflow, air that's going up and over the outflow from the forward flank. And the blue, of course, is the outflow. And on the right-hand side, the inferred horizontal vorticity. And if we look at this lowest quartile, I'm going to kind of keep a scoreboard here of a metric here of circulation. And I'm going to have two boxes here, a broader circuit here, 1 kilometer deep in yellow, and this tighter circuit here in red, that's in the lowest 500 meters. Centered again on the leading edge of this density current where we think vorticity would be the strongest. And if we look at the lowest quartile, we see a certain amount here, fairly broad distribution of vorticity. As we move into the second quartile, we see kind of a mixed bag here, intensification. I'll toggle back and forth here. Somewhat of an intensification of that horizontal vorticity and a narrowing of that vorticity as well. But the metrics are, fairly even. As we get to the third quartile, I'd argue actually we see a decrease in the strength of that vorticity, whether it's the broad circuit or the red circuit. I should say circulation, not vorticity. And then we get into this upper quartile, and we're completely in a different regime now for this upper quartile. We clearly have much stronger horizontal vorticity in play here. Some of these border on streamwise vorticity currents, and all measures of circulation show an increase. So it does seem like observationally, when we get to this upper quartile of mesocyclones, that we do see an association with a stronger horizontal vorticity on these forward flank boundaries, which is kind of a key finding. All right, so in summary here, we talked a lot about cold pools today. We talked about the processes that are relevant. We talked about slippage a little bit, accumulation of vorticity along these storm scale boundaries. A lot of our understanding comes from numerical simulations, including the CM1 simulations I showed that Alex and I have been working on. The observational verification is key. It's something I've always focused on in my group, is trying to observe the processes that we resolve in the models. And when we look at the upscale modes, I think the takeaway is that we do see association between baroclinity and this vertical vorticity from the 4 cases in year 1, and some directionality, which implies that storm relative flow is important and that we're accumulating vorticity as we come inbound to these mesovortices. And for the supercells and for Taurus, the SVC is a clear example of how the cold pool can be important. It doesn't have to be cold pool driven, but clearly it helps in the cases we looked at. And it's not present in all cases, in fact, not even most cases, but in the cases it is present. A lot of times we see visual features like that tail cloud I showed. And that last part there, it does seem like there is some association between how much horizontal vorticity we see on the forward flank boundaries and the vertical vorticity of the mesocyclone, which is in line with those simulations. All right, that was a lot, but I'll stop here and I'll be glad to take any questions.
Dr. Lisa, that's fantastic. Thank you very much. Yeah, we'll open the. That's a round of applause, Andrew. So yeah, we'll open the floor up to questions, either online or in the room here.
Steve, I have a question.
Yeah, Shannon.
So, Chris, what was the most surprising aspect of your findings? Like, what were you not expecting that you discovered?
Oh boy, that's great question. Yeah, you kind of go into these projects and you're kind of letting the theory and the numerical models guide your your expectations. And I guess, I mean, I could probably say something for each of these modes, but I overall I was kind of pleased that we were able to resolve, for example, in Taurus here, that we did see some semblance of these streamwise vorticity currents. I'd like to think that we've been observing storms for quite a while, and we really never I can't remember ever really seeing features quite like this. And it, just the fact that we have high-res simulations now showing them doesn't mean that they should magically appear. But I think maybe we just have dedicated our focus now to that portion of the storm, and with a specific type of strategy that allows us to to pull out those specific objectives. So I was surprised that we had these really strong SVC cases. I could have equally expected that we didn't see anything across any of these cases in Taurus, right? So I think that's probably what for the supercell side probably surprised me the most. Honestly, on the upscale side, I'm just pleased that we were able to collect data on QLCSs in perils. I mean, if you're familiar with our operations plan, we have to make a decision on an IOP, basically 3 days ahead of time. And yeah, I hear the groans. That's tricky, and fortunately in year one, we had some really strongly synoptically forced events that, had some predictability. But yeah, how this works, especially as you get later in the season when things get a lot more mesoscale and less synoptic. Yeah, your predictability kind of gets worse. And I'm kind of dreading that part of the decision making this year. So I don't know, that's just my quick response to that question. Wasn't that quick, I guess.
Thank you.
Here, I'll ask a quick one here. So I know some of the challenges with these field projects have been trying to get that sampling in that lowest 300 or 500 meters. So you do pretty good at the surface, and then we do pretty good aloft. It's trying to find those key details in between. So I mean, it's good to see increased soundings and then the use of UAS. So how do you see the evolution of fieldwork to try and capture more of that? 1 to 300 meter layer.
Oh, that's great question. Yeah, I think radar technology has certainly evolved. We have a great tool at Texas Tech with the KA band, since we can see close to the ground without getting clobbered by the ground contamination there. I think as you go forward, you're going to see this, further advances in radar technology. I think, rapid scanning radars, imaging radars that can kind of help us out with those types of things. The catch on those right now is that the beam width is just kind of large on those types of systems, which kind of prohibits our, collection near the ground. So, but certainly the temporal resolution is great. And some of these processes are really transient that we're talking about. So, certainly I can see that helping out. Yeah, UAS has been a huge help. One drawback, I didn't really go into depth on this, but in Taurus 19, we had some issues with the aircraft, that they weren't aspirating properly, so we weren't quite capturing the gradients like we had hoped we would. We made that modification, and I say we, but it's really University of Nebraska and Colorado that were working on that part of it. They moved the sensor. Everything was all set. We were excited for 2022. Yay, COVID's over. And a week before the Taurus 22 started, there was an incident where there was a crash with one of the aircraft and it started a fire, and the aircraft were grounded. So, the aircraft didn't even fly in 22. Which was a real bummer, because I think it would have been a major contribution. So we're hoping we get a shot here next spring to try to specifically get unmanned aircraft in. But yeah, profilers are going to be a big part of this. Perils is littered with profilers to try to get that lowest kilometer in particular. Obviously, Upsons help us out with that as well to some degree. So yeah, it's but I think there's room for creative solutions to this too. We've talked about some other ways we can try to measure baroclinity more directly, but yeah, sorry, it was a long-winded answer.
No, that's okay. We lost the screen here for a second, but
We have it behind us.
we have it behind us, so we're okay.
Okay.
Is there any other questions online or in the room? Or
Yeah, I have one. I'm just curious, with all the data that you're gathering in the field, do you ever get a chance yourself to actually get out and join that crew?
You mean outside of the project itself, or yeah,
Just
well,
actually just get out there yourself and join the group. Is it all
Yeah.
students, or do you get out there?
it's a funny thing about COVID. All our projects were grounded for 2 years. Actually, it was the first time in more than a decade that I actually got to go out and actually chase storms on my own. And actually took my son out there, and we saw a couple tornadoes. Kind of reminds me of the good old days, I guess. But yeah, that's the nature of the business nowadays. May and June come around, and you've got projects to do. So I don't do a whole lot of recreational chasing, not as much as I'd like to do. But yeah, that's a great question. I know the spirit of your question, definitely.
Thanks. Yeah.
Mm-hmm.
since we're getting past the top of the hour, I'll table my question about trying to get more equations later.
Okay.
So again, Dr. Weiss, I want to thank you for joining us this evening and for giving us this great presentation. We will contact you later to get you an Amazon gift card for
Oh, thank you. I appreciate that.
Yeah.
No, it was absolutely my pleasure, and I'm glad we were able to make it work out before Perils got going here next month. So thanks for having me.
Yeah, you're welcome. So I guess just to wrap up some other chapter business real quick. First, to note that we're not rotating locations anymore. We will be sticking here at the North Central Texas Council of Governments building for the rest of the year. We appreciate the folks at UT Arlington for hosting this for a couple months while we were trying to figure things out, as we were also trying to get out the COVID stay at home for the last few years. I reached out to the local science fairs. They'll be happening next month around I think it's the 18th and 20th of February. I just started getting information in this evening right before the meeting, so I'll pass it along, and for those who are interested in volunteering, I can get you the information for that. Other than the typical chapter dues, if you haven't had them in, is there any other chapter business we need to take care of?
I've got the envelopes with prizes. What you want to do. I guess I can give you the prize money next meeting next month.
Maybe, but I think the meeting is happening after the science fair. So we'll figure it out.
Okay. We can be.
Yeah. Dave, anything on your end?
I do not have any other topics or agendas, so yeah, I think we're good. Thank you,
Okay.
everybody.
Yeah, thank you all. This meeting is adjourned. We will see you next month. It'll be the 21st of February. So y'all have a good night.
Take care, everybody.